And I'm not going to talk about data at all. I'm sorry, I'm just going to talk about tools. But I totally agree the data are the foundation. And without the data, you can't really have a model. So these models here are based on the measured data. So I'm going to talk about a statistical learning framework for groundwater nitrate models in the Central Valley, California. And I'd like to acknowledge my collaborators. A few of these are in the room, I think, and I like the idea of building on the accomplishments of others. So the outline of the talk is I'm going to talk about machine learning with an emphasis on ensemble tree methods. And then I'm going to talk about statistical learning as a way of preventing overfit, and talk about comparative models for the Central Valley nitrate data set that we have collected. So I did mention the word data. And finally talk a bit about the interpretability of the results, because there's a conception with machine learning methods that they're not they're black boxes, but I think we can maybe push that a little bit and see if we can use these for a certain amount of interpretation. So we'll see. Before talking about ensemble tree methods, I think it's useful to talk about a single classification tree. So this is a method known as CART, which is classification and regression tree analysis. And this is a small portion of a really big tree that was done for another data set. There I go again. National data set from USGS NAQUA program. So you're just looking at a portion of the tree, but a basic idea is that it's binary recursive partitioning. So the idea is to do a split of the data on a variable that best explains or most reduces the sum of the squares between the parent node and two child nodes. And we keep doing this in recursive fashion going down the tree to some stopping point. And in this example here, we have nitrate concentrations here at the top. A split is done based on chloride, high chloride. This particular node, there's your nitrate concentration in milligrams per liter is N. Now we do a split based on the permeability of soils, on DO, dissolved oxygen, and then permeability. Again, you can see the nitrate concentration increasing as you go down these nodes. So the tree is very intuitive and it's simple to use. The idea here is that we're using many such trees rather than a single complex tree. We use a lot of simpler trees or weak learners in an additive model. And just focusing on the tree methods for this as a type of machine learning for the moment, there's lots of advantages to doing it this way. The relations need not be linear, monotonic, or even follow a particular data distribution. We can screen large numbers of variables with these methods, so it's data mining, if you will, a couple hundred variables. Makes no difference. The methods can handle them. Not that we would keep all of those, but you can certainly start with a large number of variables. The methods handle missing data. They're not greatly affected by collinearity, so you can have variables in the regression model that are rather strongly related to one another. And the methods automatically incorporate interactions. The disadvantage of machine learning methods is that it's pretty easy to overfit the data. Also, with ensemble trees, the result is an aggregate of many trees, so you can't just look at a single tree and figure out what's going on like we could in the previous slide. And finally, there is this perception, these methods tend to be black box, and that's what I'd like to try to challenge today a little bit towards the end of the talk. So for the Central Valley nitrate data set, groundwater nitrate data set that NAQUA has collected, we looked at various methods here and did a comparison of their ability to fit the data. So several of these were machine learning methods such as boosted regression trees, random forest regression. These are the ensemble tree methods. We also looked at Bayesian networks, artificial neural networks, and then also hypothesis-driven approaches such as multiple linear regression. And most of these were done in R, and Bayesian is Netica software that Mike Feenan has attached a cross-validation wrapper to it to do cross-validations. So these are the models that we evaluated for nitrate concentration, and we also were interested in methods of predicted nitrate probability. So again, you can use tree methods for here, but there's slightly different formulations. So in this case, the boosted regression model, rather than a Gaussian formulation, is Bernoulli. You can get probabilities from that. And random forest classification will get you probabilities. And then for the hypothesis-driven approach, we also took a look at logistic regression, which we have used a lot in the NAQUA program. And as far as the machine learning methods go, we're taking advantage of a method called CARROT, in our package called CARROT, by Max Kuhn for classification and regression training. And this is a way of implementing the statistical learning, which was in the title of the talk. So we find that as the models get more and more complex, it's possible to overtrain. And how do you control that overtraining? And we tend to do this through machine learning methods don't have traditional parameters, and there's no hypothesis testing. So we tend to do this through what we call meta-parameters. For example, with boosted regression trees, and the depth of the tree would be a meta-parameter that controls the complexity. The deeper the tree, the more complex it is. We want to try to control or constrain that complexity. Shrinkage is learning rate. There's number of trees, the number of observations in terminal nodes. So these are things that you can use in CARROT to control the complexity of that method. For random forest, it's the number of predictor variables tried. For artificial neural networks, you can look at numbers of hidden layers and numbers of nodes on those. And then for Bayesian networks, it's number of input, latent, and output bins. Well, here's the statistical learning part. So if you put this complexity on an x-axis here, like we've done here, and then you have a fit metric such as r squared over here. Now with these methods, you can train them up to r squares of 1 essentially, but this is not good for predictive performance. So when you go to apply the model to new data, you really need to dial back that complexity, and that's what we're trying to show in the testing curve. So for each level of model complexity, we do a k-fold cross-validation. So we have a testing r squared and a training r squared. And as we increase complexity, what we're looking for is kind of a sweet spot here. And if you get too complex, then the performance is going to degrade. The fit performance is going to degrade on the testing side. So this is what we're looking at here, not this so much. So focusing on this, you could say, well, this is my best model because it's got the maximum testing r squared. But we also, we put one standard error bands on here, and we take a look at models that are within, simpler models that are still have an r squared within one standard error of the maximum testing r squared. Sometimes this has benefits for holdout data that are sequestered and not used in training or cross-validation. So how does this work with real data? So again, this is a Central Valley groundwater nitrate data set, and in this particular paper, there were 3 methods being compared to Bayesian networks, artificial neural network, and the boosted regression trees. And this is the training part of the cross-validation. So, and as I said earlier, you can take these r squareds up to 1, and it looks great, but it doesn't really do you that much good in terms of testing performance. And we also see that the boosted model tended to outperform the neural network and the Bayesian network methods for this particular data set. So let's look at the testing performance here, and this is more of what we would expect for prediction. And the r squareds are lower, and these are 1SE bands on the r squareds. And here's your different levels of model complexity here. And we didn't see it so much with boosted, but you do see kind of a degradation of performance with these other methods here as you get out to high levels of complexity. And you could look at the maximum r squared models here, and we also looked at the 1SE models and found that in a couple of cases the 1SE models perform better with holdout data. So here's the, I guess the proof is in the pudding. So here's performance with the data set for cross-validation tuned methods using the statistical learning framework, which we apply to the machine learning methods. And we have training data and testing data. I'm sorry. Now, in this case, this is not cross-validation testing data. This is actual sequestered data that was held out, not used in any of the model training or cross-validation. So it's a little bit more of a rigorous test of predictive performance. And for this data set, the boosted regression trees did best in terms of holdout R squared, and that's mean square error over there in the last column. And oops, sorry. And these models are basically ranked by the holdout R squared. And we also did this for our probability models, but now we're not looking at R squares. We're looking at things like total percent correct of samples exceeding some threshold. In this case, it's 4 milligrams per liter of nitrate. And sensitivity is the ability of the model to predict true positives, and specificity, same thing for true negatives. And again, you can train these models up very high accuracy in the training side, but once again, we're really focusing on the holdout performance, predictive performance, and tuning the models to try to optimize these statistics here. And these have been ranked by total percent correct for the holdout data. And we can use our models then for predictions. So we optimize the models for predictive performance. Now we're using them for prediction to extend our monitoring results to the unsampled areas. And this is for the Central Valley. Obviously, this is the boosted regression tree model. And this map was made for domestic well depth, where the median of the perforated interval depth was 31 meters. And you can see colors here corresponding to, this is a concentration map now, not a probability map. So the reds are higher, reds and pinks are higher concentrations, and we see these predicted values now tend to be in the eastern fans, more extensive on the eastern fans, which are more oxic, and you have more reducing conditions in the center of the valley and in the Sacramento Valley. Now, as far as interpretability, okay, there's a couple of things going on with this slide. One is the idea of a partial plot, which you can make, which helps you see the influence of your predictor variables on, in this case, it's predicted nitrate concentration. This is natural log of concentration here in the y-axis. The other thing that's going on is that with our models, we are using hybrid approaches where we use outputs from other models, more physically based models. In this case, it's Claudia Font's ModFlow model for the Central Valley. So we've got this model for the entire Central Valley, so why not extract variables from it that we can use in our statistical water quality models. So Claudia extracted the vertical water fluxes in the upper active layer. And the 1992 water year was considered typical when we did this. Nitrate data are for the 2000s. And so I want to point out that, okay, these negative fluxes are downward. So as you go increasingly negative, you have more downward gradients in that upper active layer. And we see a little bit of a bump here for nitrate in that case. So we have these compiled for monthly. And this is starting in November, so I'm just going to progress through the months, and we'll take a look and see what happens. And this is December, pretty much after the irrigation season, obviously, and the response is pretty flat. January, February, March, and then here, I would say this is probably a pre-irrigation. I don't know if Karen Burroughs in the room, or but people that actually live in California. I live in Virginia, sorry, but some distance from the site, but that would be pre-irrigation, I believe, and you can see a response in the nitrate. And then you get into more the middle of the irrigation season, and things ramp back up in terms of predicted. These are predicted nitrate concentrations by our model. Again, this is a partial plot. And then in October, the irrigation stops, I believe, and things start to ramp back down in November. So I would argue that the methods, or machine learning methods, perceived as black boxes, but they are interpretable if you use the tools, in this case partial dependence plots, to try to extract meaning for your predictor variables. Concluding, statistical learning mitigates the tendency of machine learning methods to overfit the data. The boosted methods, stochastic gradient boosting is the formal name of that method, outperformed the other methods for predicting groundwater nitrate for this data set for Central Valley. And the partial dependence plots enhanced the interpretability of the results. And thanks.
Thank you for your talk. You mentioned that there were a few hundred parameters that go into this model.
Yes.
How do you represent the location? And do you have any representation of how the proximity of one location to a known data value, or how do you represent?
Location in terms of effectiveness in the model, or?
The location, like where it is it
Sure,
north of the state, the south of the state? Is it
Oh, we
close
map
to...
them. So like for the mod flow fluxes, we just do
Yeah.
a map, and you can see
So
on the
do you
map
put like
where.
the latitude and longitude? Is that?
Yes, that's typically in the model. And also we have a parameter called hydrologic position, which is how far you are from the center axis of the valley, heading towards the mountain range. So we have hydro position, we have latitude, we have longitude. These typically, the advantage of the method is you can throw all these things in, and it doesn't matter if they're correlated with one another, because it's very unlikely that they would be showing up in the same tree if the trees are simple enough, say, a depth of 2 or 3, for example. So they can coexist in the model, and then if they seem redundant, you can take some out and just get down to the essential predictors, but we just map them. We map them to see where they are, and then if I could just continue with this. This is a variable importance metric that comes from the modeling, so we can look at variables like latitude, longitude, and other things, and see how they rank out. So it's part of the usefulness of the method. So the bigger the bar, the more sum of squares reduction there is when this variable is in the model. So if you have a lot of variables and competing variables, you can get this pretty easily from the code and take a look. Yeah, sure.
I saw that you said you were doing the samples at 35 meters or so. Is that right?
35 meters. I don't remember saying 35 meters. Oh, I'm sorry. Well, we did predictions. The samples vary in depth, from monitoring to domestic well depth, public supply, a whole range. We were making the predictions. So when we made that map, we made the predictions for the median depth of domestic wells to show the potential for nitrate at domestic wells. So our objective is mapping contamination at domestic well depth and public supply well depth. But we can make it for any depth. So depth is in the model, and you can have a 3D visualization.
The question I saw that you said that one parameter it changed depending on the time of the year. And I wondered,
Yes.
You said it was post-irrigation or pre-irrigation.
Right.
Is the irrigation going to affect the water and groundwater within that time period?
Well, no. There's more likely a plume at depth, and it gets pulled down as the gradients increase. So it's already at depth. It's not going to make it from the land surface to the well in 1 year. It's a very good question. Yeah, good point.